Let's see if, oh, the mic does work. Can everybody hear me? Okay. I almost don't want to talk too loud or it'll be, I tend to get excited and then it'll be really loud. Well, thanks so much for having me. This is actually my first time on campus here. It's a beautiful planetarium, so it should be fun and it's great to see such a nice audience. Okay, so the special, this is going to be fun because I'm like this and I fall backwards with this big screen. So the special topic for tonight is these really amazing systems called globular clusters. So this is an image of one of the many globular clusters in the Milky Way that was taken by the Hubble Space Telescope. And as you can immediately see just looking at this image, I think the most visually striking thing about these globular clusters is that in their central regions, the stars are packed together very tightly. The central regions are incredibly dense. In fact, these are some of the densest regions of stars in the known universe. And as I'm going to talk about tonight, these very high densities are completely different than the sort of local density of the galaxy where the sun lives. And this sets the stage for all sorts of interesting astronomical phenomenon that would never happen for a star like the sun, which lives in a much more benign part of the galaxy. So to give an idea of how dense these clusters are, let's zoom in on the center, what we call the core of the globular cluster. And the typical size of one of these globular cluster cores, the central region, is about a parsec in radius. Now, for reference, 1 parsec is roughly the distance between the sun and our closest stellar neighbor, Proxima Centauri. So just for fun, we imagine the sun was at the center of a globular cluster, which it very much is not, as we'll talk about later. Proxima Centauri would be right around here. So within our local volume, enclosed by a parsec, we have 2 stars. We have the sun and Proxima Centauri. But as you can see in a globular cluster, the same volume enclosed by 1 parsec contains hundreds of thousands of stars. So these environments are way, way denser than anything we're used to in our own sort of neighborhood of the galaxy. Okay, so this is a sort of an edge-on simulated image of the Milky Way. So we see the disk of the Milky Way. Our sun is in the disk of the Milky Way. The disk is very low density. The sun is around 8 kiloparsecs from the center of the galaxy, where we have the galactic bulge. The center of the galactic bulge contains a supermassive black hole, which is a topic for another night. But if you look at the halo of the Milky Way, this sort of roughly spherical region in the outer parts, this is where the globular clusters live. So there's some globular clusters that are found in a disk. You can see these in the disk as well. But most of the clusters are found in the halo. They are roughly spherically distributed throughout the halo of the galaxy. And in total, there are roughly 150 globular clusters that we've observed in the Milky Way. So these are very common types of systems. But in the past couple decades, in large part due to telescopes like the Hubble Space Telescope that have allowed us to look at other galaxies outside the Milky Way, we now understand globular clusters are not unique to the Milky Way. They're actually observed in essentially all types of galaxies that we know of. So this spans all the way from the lowest mass galaxies, ultra-diffuse dwarf galaxies. These contain, instead of 100 globular clusters, maybe a handful or maybe a couple dozen globular clusters. Spiral galaxies like the Milky Way contain 100 or several hundred. So for example, Andromeda, which is slightly more massive than the Milky Way, contains around 500 globular clusters that we can observe very easily. And then the most massive giant elliptical galaxies, so Messier 87 is a classic example in the local universe, contain thousands, even tens of thousands of these very dense globular clusters in their halos. So these are observed in all types of galaxies. Now, another defining feature of globular clusters, aside from their very high densities, is they're also very old stellar populations. So the Milky Way's globular clusters contain not only some of the oldest stars in the galaxy, some of the oldest stars that we know of in the universe. So these were formed a very long time ago when the universe was very young. So what this means is when we look at these globular clusters in nearby galaxies, we're looking at very old systems. So another really cool recent advance in this field came just in the past few years. As many of you have heard of, the big new shiny toy for astronomers is the James Webb Space Telescope. So the James Webb Space Telescope is allowing us to see further into the universe than ever before. Now, of course, as we look further out into the universe, we're also looking back in time because it takes light a finite amount of time to reach us here on Earth from the very distant reaches of the universe. So when we look at structures, galaxies, clusters of galaxies in the very distant universe, we're looking at these galaxies not as they are now, but as they were millions, even billions of years in the past. So if we zoom in, this is one of the first sort of science images taken by the James Webb Telescope right when it came online. So every object in this field is a different galaxy very far out in the universe. But if we zoom in on this little box here, we see this particular galaxy has these little sort of small circular blobs around the outer part of the galaxy. And we think these are actually some of the most distant and therefore also youngest globular clusters that we've ever observed. So not only do we know of globular clusters in other galaxies, we also now have observed globular clusters in very distant, very young galaxies. So all sorts of really cool recent science advances in this field. These are sort of, you can think of these as sort of the infant or baby versions of the very old globular clusters that we observe in the Milky Way. Okay, so let's think about the life of a star living in a globular cluster. So we'll start with the sun, which again is not in a cluster. So the sun, again, our closest stellar neighbor at Proxima Centauri is a parsec away, which means for all intents and purposes, the sun is by itself. There are, of course, planets orbiting the sun, but from a stellar perspective, the stars are very far away. They exert no important influence on the evolution of the sun. Now, the sun is actually kind of an exception as a single star. Most stars that we observe in the Milky Way galaxy are actually members of binary pairs. So these are pairs of stars bound gravitationally that orbit one another throughout their lifetime. So, we've upped the complexity by 2 times, but these are still relatively simple. The orbits follow what we call Kepler's laws. These are very well understood relations. The stars are orbiting around one each other, but most binaries that we observe are very wide, so the stars aren't really interacting with each other aside from their gravitational interaction. But in globular clusters, again, because we have stars and also binary stars packed in these very high densities, you can have groups of stars form larger hierarchies, 3, 4, 5 stars bound together at once. And once we go to these larger hierarchies beyond pairs of stars, we start to get chaotic types of interactions and all sorts of fun things that would never happen for isolated stars like the sun. So let me show you an example. So what I'm going to show you here is an animation of a single star like the sun coming into gravitational contact with a binary star. And this is the type of encounter that happens all the time in these globular clusters. So here's our sun, here's our binary. And once you form this group of 3 bound objects, then you get chaotic encounters. So you can see occasionally a little mini binary will form, but that third star always comes back in and sort of interrupts the dance. And these types of encounters are happening all the time in clusters, and they essentially proceed until a few different things can happen. In this case, the outcome is actually a collision of 2 stars. So one of the really cool things that can happen in globular clusters, a direct result of the very dense environments, is stars can collide with each other. There are lots of observed evidence of these stellar collisions happening in many of the different globular clusters that we see in the Milky Way. Okay, so let's sort of put this all together. This is going to be now a computer simulation of what we call an n-body simulation of a globular cluster. So essentially we're going to have one particle for every star in the simulation. We're going to press go, and we're going to see the gravitational encounters of all the stars with one another as they evolve over time. So, of course, this is sped up quite a bit compared to reality, but there's a few sort of takeaways we can get from looking at this animation. So I want to draw your eyes to 3 different things. So the first, if we just sort of look at the system as a whole, we can get an immediate sense of the sort of chaos inherent in these systems, right? The other thing you can do is if you just pick any star in the simulation, it doesn't really matter which one, and you sort of watch it evolve, you can see the orbit of the star is actually changing over time. Occasionally, a star comes close to another star, and it sort of gets slingshotted around and abruptly changes direction. So these very close gravitational encounters that significantly perturb the orbits of stars is actually what causes these clusters to settle into their spherical or globular shape. This is how they get their names. So the other thing that you'll see is occasionally you have these sort of really big red stars appear out of nowhere and then disappear. So does anybody know what this is? Any ideas?
Stars growing up.
Yeah, exactly. So these are stars evolving over time. As stars evolve, they become red giants, and eventually they collapse into compact objects. So this is the next part of the talk. So let's talk about a very quick detour into the evolution of stars. So this here is a simulation of the evolution of a star like the sun. So as stars evolve, you essentially have this very delicate balance between gravity and energy generated by nuclear fusion in the center of the star. Gravity is pushing in, the energy generated is producing an outward pressure. But eventually the nuclear fusion, the nuclear fuel in the core is exhausted, at which point there's nothing to prevent the collapse of the star from gravity. And as sort of a last gasp of the star's life, it expands into a red supergiant, and then eventually the envelope is expelled entirely, and the center of the star collapses once the nuclear fuel has been exhausted entirely. So for a star like the sun, a relatively low-mass star, the fate is collapse to a white dwarf. So the center of the star, once the nuclear fuel has been exhausted, is for the star to collapse into a white dwarf, which is supported by a different type of pressure called electron degeneracy pressure. So this is the fate of something like 99% of stars in the universe, to become a white dwarf. But for more massive stars, okay, so white dwarf. So more massive stars, so these are stars that are 10, 20, 100 times as massive as the sun. Because the temperatures in the center of the star are much hotter, as a result of the much higher masses, they're able to burn together and create heavier elements, carbon, oxygen, neon, iron. And this allows essentially a much more energetic outcome called a supernova explosion. In this case, we go through the same evolutionary stages, the nuclear fuel gets exhausted, the star expands to become a giant, but instead of the central region collapsing into a white dwarf and the outer envelope being gently shed out into space, we have a much more violent event called a supernova. And in this case, the central core of the star collapses into a much more extreme stellar remnant, which can be a neutron star, or for the most massive stars, it can collapse into a black hole. Okay, so this is sort of the family portrait of the different types of, compact objects, or the different sort of regions of the stellar gradient that you can think about this. So again, low-mass stars, stars like the sun, will ultimately become white dwarfs. Increasing in mass, things that are roughly 5 to 10 times the mass of the sun will become neutron stars. And then the most massive stars, these are stars that are 50, 100 times the mass of the sun, will ultimately end their lives as black holes when they collapse. So a fun little sort of illustration of, to give you an idea of the densities of these different objects. So, I don't know, maybe there's 60 or 70 people in this room right now. So if I took everybody in this room and I gathered us and had us all pile into a typical elevator, right? Maybe we could do it. It'd be really, really tight, but maybe we could do it. So that's about the density of a typical star. About 100 humans in the size of a single elevator. So in order to achieve a density comparable to a white dwarf, I'd have to take every human in the entire world and pack them into the elevator. And if I wanted to make a density comparable to a neutron star, so you can see here, this is a neutron star compared to a typical city. So neutron stars are usually around 10 kilometers across. I would have to take the same elevator, which is filled with the entire human population, and squish it down to about the size of a sugar cube, about a square centimeter, a cubic centimeter. And then a black hole, of course, is even more dense. The black hole is sort of infinitely dense. It's so dense that the gravitational pull is so strong that even light can't escape, which is why they're called black holes. So these compact objects are dense beyond belief, dense beyond anything we have experienced with here on Earth. But in all instances, these are observed out in the universe. These are real objects, which is kind of cool to think about. Okay, so what I'm going to do next is I'm going to sort of combine these things. We're going to take globular clusters, these incredibly dense stellar systems, and we're going to take compact objects and put them in these globular clusters. And now we sort of have the stage set for some really cool stuff, because we have black holes, which are, kind of the coolest thing you can think of in astronomy. And they're living in these really dense environments. So they're going to do all sorts of fun stuff. The black holes can collide with stars, the black holes can collide with each other, produce all sorts of really fun outcomes. So let's talk about how this works. So let's think about a typical globular cluster right when it's born. So before any black holes have formed, before any white dwarfs or neutron stars have formed, we just have an initial population of roughly 1 million stars. Typical globular cluster. So as you can see, any initial distribution of stars has a range in different types of masses. Most of the stars are low mass like the sun, and a smaller number are massive. And very quickly, through the evolution of the cluster, the most massive stars are going to exhaust the nuclear fuel and they're going to collapse into black holes. So this usually takes maybe a few million years, maybe 10 million years. Now, as it turns out, for a typical population of stars, roughly 1 out of 1,000 stars is massive enough to collapse into a black hole. So if we have a typical globular cluster with around 1 million stars, around 1,000 of these stars will be massive enough to form black holes. So think about those pictures I was showing earlier at the very beginning. Each one of those globular clusters we think has around 1,000 black holes in it. Now, these black holes, once they form, are very massive compared to the other stars in the system. So as a result, they do something called mass segregation. This is essentially analogous to the reason that denser fluids sink to the center, to the bottom of a glass of water, for example. Gravity always brings more massive objects to the center of the gravitational potential well. So the same thing happens in a cluster. The most massive things sink, the black holes sink to the center. So the outcome is essentially the formation of this very dense central subsystem composed almost entirely of black holes. There's a few stars mixed in, but it's essentially composed entirely of that population of 1,000 black holes. And that black hole subsystem is even denser than the sort of normal luminous part of the stellar cluster. So again, this is giving us an opportunity for all sorts of really fun phenomenon as a result of the very high densities. So throughout the remainder of the evolution of the cluster, the remainder of its lifetime, you have many types of black hole interactions and also black hole star interactions taking place. Okay, so this is sort of like a cartoon illustration. So what I want to do next is I'm going to show another one of these computer simulations of a globular cluster. But now we're adding in black holes. So we'll see how this shows up. It might be a little hard to see. Yeah, you can kind of see the black holes. The black holes are black. I should have made them a different color for artistic purposes. But anyway, you can kind of see them in there. So I want to, again, draw your eyes to a few things. So the first thing you can see is the black holes are interacting with the stars. And again, because a black hole is much more massive than a normal star, when a black hole comes into close gravitational contact with a star, it essentially slingshots the star away. More massive things have more energy on average, so they try to exchange energy, and the result is to kick the star, essentially. So the black holes are transferring energy to the stars. The second thing you'll see, the black holes are also occasionally interacting with each other and kicking each other. So actually, even though every cluster begins with around 1,000 black holes, that initial population of 1,000 slowly decreases over time as the black holes kick each other out of the cluster that they live in. So the number of black holes slowly decreases over the evolution of the cluster. And then the third thing you'll see occasionally is pairs of black holes form that are stable binary pairs. So I showed an illustration of a binary star a few slides ago. In clusters, because of the fact that they're very dense, pairs of black holes can form binary black hole systems. We'll come back to these a little bit later. Okay, so you very well may ask, if you're a good scientist, well, this is all kind of fun, but how do we know this is actually happening? I've shown some kind of pretty, simulations of things, but maybe I'm just, having fun on a computer and, making fun videos. So can we actually observe this? How do we know real globular clusters actually have black holes? So again, black holes are black. We can't observe them, so how do we know they're there? So I'm not tricking anybody. We actually do have very good observational evidence that globular clusters have black holes. There's a few ways that we can observe them. The basic idea is, of course, you can't observe a black hole directly by definition because light can't escape a black hole. But if a star or some other type of luminous object orbits around a black hole, then, of course, this orbit follows very well-known mathematical relations, the same equations that govern the orbit of the Earth around the Sun. We can use these equations if we can observe the position and the velocity of the star over time as it orbits around the object to infer the mass of the thing it's orbiting, even if we can't see the thing it's orbiting. So, for example, just from the orbit of the Earth, we can measure the mass of the Sun without ever observing the Sun itself. The same basic idea can be used for these systems to use a star orbiting a black hole to learn about a black hole that's there that we would not be able to see otherwise. Now, in practice, this is really hard because, again, a typical globular cluster, for example, has 1 million stars. So in order to find, the lucky star that has a black hole binary companion, we have to observe every single one of the 1 million stars in the cluster over a pretty long period of time to map out its whole orbit, which would be really, you'd have to have a really good telescope and a lot of money to use the telescope for that long. So it would be very difficult. But, well, I guess there's good funding in astronomy, so we've actually done this. The first one of these black hole star binaries was found in a Milky Way globular cluster in 2018. This was really exciting for me. This was, I think, the second year of my PhD at Northwestern. So this was a exciting event in astronomy. So this was actually one of the things that sort of set me on the career path I'm on now. I thought this was really cool, so I thought, okay, well, I'm going to build computer simulations of globular clusters to see how these things form. Okay, so this was found with, it's called the Very Large Telescope, kind of a funny name, very creative, which is down in Chile. And they found the first ever black hole formed from the collapse of a star in an orbit with another luminous star. And this was found in one of the Milky Way globular clusters. So this was 2018. Again, this discovery came out. I started working on this. I made some computer simulations of one of these globular clusters with black holes inside, similar to the sort of animations I was showing before. And one of the predictions for my simulations was there probably are actually more than one. There's probably actually maybe a few, maybe 5 or so of these. So we published our result predicting there should be more. And then this telescope team went back and did some follow-up observations, and then they actually found 2 more black holes in this particular globular cluster. So these are similarly black holes in orbits with stars in the center of this globular cluster. So this cluster has 3 of these black hole star binaries. Now, there's another way to observe this, and this is sort of the original, the first way that we observe black holes in the Milky Way. So the binaries I was showing on the previous slide were what we call detached binaries. So here the star is on a pretty wide orbit around the black hole. So the black hole is exerting gravitational influence, but it's not really, violently perturbing the star. But if you have a very close binary, that's now what we call an interacting binary, so no longer detached, the star is close enough to the black hole that the black hole can rip material off the star, which then does violently perturb the star. So these are something called X-ray binaries. And this is sort of another way you can observe a black hole. So as a star expands, as it becomes a giant, eventually its radius becomes big enough for the black hole to pull material off the outer parts of the star. As the material inspirals onto the black hole, it's formed something called an accretion disk, which you can see once it comes around the other side. There we go. And these accretion disks, as the material falls onto the black hole, are incredibly hot, which means they emit very predominantly X-ray radiation. There aren't a lot of things. X-ray radiation is kind of rare. So this was the first way black holes were actually discovered in globular clusters. People pointed X-ray telescopes at globular clusters, and they found these weird X-ray sources, which sort of very clearly stood out from everything else. And we understood that those are actually black holes pulling material off of binary companions in very close orbits. So there's about 5, there's actually about 6 or 7 of these now, known in different Milky Way globular clusters. So these are X-ray binaries where the black holes are gobbling up material from their stellar companion. Okay, so there's actually another way that's a little bit more of an indirect method of observing black holes in clusters. And those 2 methods I showed on the previous slide were observing individual black holes that have binary companions. There's also another way to observe the sort of full population of hundreds or even thousands of black holes in the centers of these globular clusters. So what we can do is take advantage of the fact that when these black holes live in clusters, they're exerting an influence on the luminous stars. Again, the black holes are sort of exchanging energy with the luminous stars in the cluster. Okay, so the sort of best way to characterize a globular cluster as a whole is with what's called a surface brightness profile, or really just a density profile. So this essentially, these 2 plots, are just simply showing the density in the cluster versus radius. And of course, as you can see, if you look at these images, you can see this very clearly. The central regions of these clusters are by far the most dense, and indeed in these plots you can see the density is increasing toward the center. Now there's two distinct types of globular clusters that we observe in the Milky Way. Every cluster can be sorted into one of these two groups. So the first group on the left here are what we call cored globular clusters with cores. And we know it as a core because you can see if you look at the density profile or the brightness profile, the central region you can see starts to flatten out as it gets close to the center. That flat part is called the core. It's a constant density region in the very center. Roughly 80% of globular clusters in the Milky Way have cores like this. And in fact, that cluster that we saw the black holes in has a very large core like this. So the other 20% of clusters are what we call core collapsed clusters. So here you can see the density increases all the way to the center. There's no flat part in the center. So it's kind of analogous to a star. A star, the core of a star is supported by, against gravitational collapse by nuclear fusion, the energy generated from nuclear fusion. We think something similar is operating in globular clusters. The clusters that have these very well-resolved flat density components, these cores, we think have some internal energy process that's halting the collapse of the cluster against gravity. And what we now think is that the mechanism for this energy generation is that subsystem in the center of black holes. Because the black holes are so massive, because they're so energetic as they interact with one another and also with other stars, they essentially are injecting energy into the regular, normal, luminous star part of the cluster, creating a core. The clusters that have undergone core collapse, we think have gotten rid of all their black holes. There's now nothing to prevent the center of the cluster from collapsing under gravity, which is why the density increases all the way to the center. So let me sort of explain how this works a little bit more. So again, every cluster is born with a population of 1,000 black holes from the collapse of the massive stars. When the black holes are there, the center of the cluster has a very flat density. As the number of black holes slowly decreases over time, again, black holes kick one another out through mutual gravitational interactions. As the number of black holes decreases over time, the density profiles becomes more and more steep until eventually, after all the black holes have been injected, the cluster reaches a core collapse state. So core collapse is the fate of all clusters. But again, because about 80% of the clusters that we see today are not core collapse, they still have cores, we think most clusters still have dozens, even hundreds of black holes left over from that initial population of 1,000 in their centers today. So most globular clusters have dozens to hundreds of black holes in their centers. Now, again, there are roughly 200, 150 to 200 globular clusters in the Milky Way. Each one of them contains maybe 100 black holes. That's a lot of black holes potentially. But again, we've only observed about 10 of these, maybe. So there's 3 of these detached black hole star binaries, and maybe another 6 or 7 X-ray binaries. So we've observed 10, but I'm telling you there's probably thousands or even tens of thousands. So why can't we find more of these? Well, it's still a relatively new field, so I think we've only just started we've only just uncovered the tip of the iceberg for what is possibly there. So I've actually started one of the main programs I'm leading at UC San Diego, is sort of the first search of Milky Way clusters to try to find more of these black holes. So we're using the Keck telescopes in Hawaii, which are sort of some of the best ground-based telescopes that we have in the world, so 10-meter telescopes. They're very powerful instruments. And we're using this special instrument called the Keck Cosmic Web Imager. So essentially what this is what we call an integral field spectrograph. So essentially what we do is we have a field of view for the telescope, which is divided into a bunch of pixels, as I showed in sort of this blue grid here. As it turns out, the size of this field of view is roughly similar to the core of a globular cluster. So as it also turns out, each one of these pixels in the instrument is roughly the same distance between the spatial distance between stars in a globular cluster. So essentially what this instrument allows us to do is slap the field on the center of a globular cluster. Within each pixel, we can measure a spectrum for the star in that pixel. This allows us, using the Doppler effect, to measure the velocity of the star in that pixel. And if we do this over enough nights, we can sort of piece together the change in the velocity of the star over time. So this sort of plot in the center, I'm showing a bunch of different points for one of these candidates we've identified. And essentially, if you get enough points, you can map out the orbit of the star, and again, this is sort of what I was showing before. If you can map out the orbit of the star, you can figure out what it's orbiting. You can figure out if it's orbiting something small, like another star, or if you're lucky, find a star that's orbiting a black hole. So this is the way that those initial black holes were discovered that I mentioned before. So essentially, we're doing a survey of a number of different Milky Way globular clusters, trying to search for, the needle in the haystack, the handful of black holes the handful of stars that are lucky enough, or you could say unlucky enough, to be in orbit around black holes. Okay, so in the sort of last little section of the talk, I want to circle back to this idea I touched on earlier. So one of the other consequences of these very dense black hole subsystems in the center of globular clusters is not only can black hole star binaries form, but occasionally black hole binaries can form. Pairs of black holes that are gravitationally bound together. So you can kind of see it there. It's a little washed out, but you can see it. So when pairs of black holes are bound together, they orbit one another, and because of essentially the extreme gravitational fields, they produce ripples in space and time called gravitational waves. So these gravitational waves are emitted, they spread outward throughout the universe, and they essentially remove energy from the binary orbit, which causes the pair of objects to spiral in towards each other until they eventually merge together, as we saw here. So the idea, if you can measure these ripples in space-time, if you can measure these gravitational waves, you can use the information carried by these gravitational waves to learn about the black hole binary and the black hole binary merger that occurs. So this was originally proposed by Einstein over 100 years ago. Of course, at the time, it was kind of viewed as, not necessarily crazy, but certainly something that could never be observed, because the prediction was the size of these stretches in space, these ripples in space, was so small it would have taken unbelievably, unfathomably sensitive instrument to ever measure these. But people, over the decades embraced this challenge, and they built such an instrument. And in 2016, almost exactly 100 years after Einstein originally proposed the existence of gravitational waves, we detected gravitational waves for the first time. So this is an instrument called LIGO. It's the Laser Interferometer Gravitational Wave Observatory. Essentially, it uses a pair of arms, so you can see this sort of L shape here, this L-shaped detector. Each one of these arms is several kilometers in length. Essentially, how this works is you shoot a laser down each arm, and at the end of the arm is a mirror that reflects the laser back. And as a gravitational wave passes through, the arms sort of stretch and pull a little bit from the gravitational waves, which means by the time the lasers come back to the center, they now are they've traveled slightly different paths, so they interfere with each other. And you can use this interference pattern to measure the frequency of the gravitational wave, the amplitude of the gravitational wave, learn all sorts of interesting stuff. So there are two detectors that were built. One is in Washington State, the other is in Louisiana. And again, in 2016, they successfully detected gravitational waves for the first time. So they detected, as we can see here, the merger, the in-spiral, the merger, and then also the ring down of a binary black hole millions of light years away out in a very distant galaxy. So this was a really monumental event in astronomy and physics and really all of science. It was awarded the Nobel Prize in Physics at the time for the huge discovery. And since this first discovery about 10 years ago now, LIGO, these detectors, have detected over 100 different binary black holes via this gravitational wave method. So this graphic here is just simply showing all of the gravitational wave events that have been detected so far, sorted in order of their mass. So this is in units of solar masses, the mass of the sun. So we can see these gravitational wave events span all the way from very low mass things, maybe with 1 or 2 times the mass of the sun. These are actually neutron stars, so there's roughly 4 or 5 neutron star binaries that have been detected by LIGO. But you can see the vast majority of these blue points are binary black holes. And these have masses spanning anywhere from 5 times the mass of the sun to, on the extreme end, over 100 times the mass of the sun. So LIGO has been an unbelievably successful enterprise, and it's provided us, it's been an explosion of information about black holes. A couple decades ago, we knew of maybe just a handful of black holes, in the Milky Way. We now know of several hundred black holes throughout the universe. So this has been a really big deal in astronomy. So, LIGO has been very successful, but there are still a lot of questions, a lot of mysteries. One of the mysteries that LIGO has uncovered that has sort of had astronomers scratching their heads is these really massive black holes up in the top right here. So these black holes that are, 50 to 100, even 200 times the mass of the sun. So these black holes have masses that we did not think should be able to exist. And the fact that LIGO is observing them suggests that there's some incompleteness in our knowledge of black holes that we need to sort of update in our understanding. So this is where we circle back to globular clusters. So another way to show this plot here is basically a distribution of the masses for all the black holes that LIGO has observed. So again, you can see most of the black holes, the peak of this distribution is at around 10 times the mass of the sun. But you see this very clear tail extending all the way up to roughly 80, up even to 100 times the mass of the sun. And this sort of gray region on the right of the plot is this region where, again, stellar evolution theory predicted black holes should not exist. Very clearly, you can see this green distribution is extending into this gray region. So these black holes form somehow. We don't know how. So one theory for how these black holes could have formed, these really massive gravitational wave events, is formation in dense stellar populations. So in a very dense globular cluster, if you have a pair of black holes merge, let's say a pair of 40 solar mass black holes that don't violate any stellar evolution theory rules, those things merge together, they create an 80 solar mass black hole. Because that 80 solar mass black hole is still living in a globular cluster, it's still living in a really dense environment, it can pair up with another black hole and merge again, and potentially merge again after that. And this sort of hierarchical series of mergers that's specifically enabled by these very dense globular clusters allows more massive black holes to form. Black holes with masses potentially consistent with these very massive gravitational wave events that have been observed. So if we take a large number of simulations of globular clusters that take into account these various black hole evolutionary dynamics, we can make this black curve here, which is one of the results from my recent work. So this is the predicted mass distribution of black hole mergers from globular clusters. And you can see, I think it's quite nice. We match very well the full distribution that's observed from LIGO. We match the peak at roughly 10 times the mass of the sun, and importantly, we also match this extended tail out to high masses. And that extended tail up to 80 times the mass of the sun is coming from these hierarchical, repeated black hole mergers that happen in these dense environments. So again, the presence of these massive black holes can be interpreted as evidence that globular clusters are contributing to the black hole merger rate in the local universe. Okay, so here's where we are now, 2025, approaching 2026. We've observed a handful of neutron star binary mergers with LIGO and several hundred binary black hole mergers with LIGO as gravitational wave sources. So looking toward the future, as LIGO continues to observe, continues to increase its sensitivity, and as we also move to upcoming proposed gravitational wave observatories like the Voyager telescope, the Cosmic Explorer telescope, the number of black holes, the size of this gravitational wave catalog, is expected to grow from the hundreds to the thousands and ultimately to the millions. And ultimately with these next generation gravitational wave observatories, we expect to be able to observe essentially every black hole merger in the observable universe. So we're very much expecting a treasure trove of insight into the properties of black holes, which is very fun for people like me and for everyone. Black holes are cool for everybody. Okay, so we're pretty much out of time, and I want to leave some time for questions. I want to just end with a fun little thought experiment. So, we've been talking about globular clusters and these incredibly high stellar densities, and the fact that they lead to all sorts of these crazy phenomena like black hole mergers, pairs of black holes and stars that are really kind of foreign to us when we just think about our, meek little sun just living by itself. So let's ask the following question just for fun. What would happen if our solar system, the Earth, and all the planets orbiting the sun lived in a globular cluster? What would it look like? What are some of the implications? So this is a simulated image. I actually know these guys. They work in Canada. They had a similar question to me, I guess, and they said, well, what would happen? What would the night sky look like on Earth if it lived in a cluster? So it would look something like this. It's not going to surprise anybody now after what I've been talking about that there are tons of stars visible, way more stars than are visible, on our normal night sky that we see here on Earth, just because there's so many stars in the globular cluster. So you might think on first glance, this would be like a dream for astronomers, right? Look at all these stars you can observe, to your heart's content. It would actually really be a nightmare for astronomers because the background light produced by these stars would be so bright. It would be like 20 times brighter than the full night sky during a full moon here on Earth. So yes, you would be able to observe the stars in your sort of home globular cluster very well. But if you wanted to look outside of your home cluster and observe the universe, it would really be all but impossible compared to here on Earth because of all the background light pollution from these many stars. So in this sense, it's good we don't live in a cluster. Okay, so that's maybe a little sad. Let's end on a happier note. So again, I mentioned at the beginning, the closest star to the sun is Proxima Centauri. It's about a parsec away. Now, in a globular cluster, the stars are packed together much more densely. The typical separation between stars in a globular cluster is about 1/100th of a parsec. So much, much closer than the stellar separation for us here in the Milky Way galaxy. So as it turns out, 1/100th of a parsec is roughly comparable to the current distance of the most distant human-made spacecraft ever launched from Earth, Voyager. So this means that if we lived in a globular cluster, the prospects for interstellar travel, or certainly for sending probes to nearby stars, is actually wouldn't be totally crazy. Or if you want to, kind of really have fun, the prospects for visiting nearby black holes wouldn't be as crazy because, again, things are so much closer in a globular cluster. So that's kind of a fun thing to think about. We can leave it on that thought, and happy to answer some questions. Thanks so much for coming. All right, questions. Should we use the microphone for questions, or we just ask?
If you could just repeat.
I'll repeat it, yeah. Okay.
Yeah, you talked about globular clusters from a very early age. How are globular clusters born? How were they made in the first place? And question number 2, we had a talk here once about intermediate-sized black holes. What you were showing there in your latest slides, would those be considered intermediate size?
Okay, both very good questions. So how are globular clusters born is the first question. So, like all stars, the stars in a globular cluster are born from collapsing molecular clouds. As it turns out, all stars, so molecular clouds are really big. And every molecular cloud, when it collapses, forms many stars. We think actually, essentially all stars, including the sun, were actually born in a cluster when they were created. But most of the clusters that are born are relatively small. Instead of containing 1 million stars like a globular cluster, they might contain 100 or 1,000 stars. So for example, the sun was probably born in a cluster with maybe 1,000 stars. And clusters with 1,000 stars, they don't survive very long. They have a very short lifetime because they're very weakly bound gravitationally. So that's why the sun is not in a cluster anymore. Its host cluster dispersed everything out into space billions of years ago. So a globular cluster is most likely born from just the collapse of a very massive molecular cloud that collapses and forms a population of 1 million stars or 100,000 stars. And then when you have this very massive stellar conglomerate, it's able to be stable and survive for a very long time, like old globular clusters. So they form in the same way all stars form, just from a more massive and more dense molecular cloud. Okay, so intermediate mass black holes. So there's 3 types of black holes, or I should say there's 2 types of black holes that we know very well. There are stellar mass black holes, which are formed from the collapse of stars. So these are things that have masses of maybe 10 times the mass of the sun. And then there are supermassive black holes that have masses of millions of times the mass of the sun. So we now know that there's a supermassive black hole in the center of the Milky Way. All galaxies, we think, have a supermassive black hole at their centers. Okay, so we have 10 times the mass of the sun, 1 million times the mass of the sun. It's very reasonable to think that there's some continuum, in fact, and that there may also be black holes 1,000 times the mass of the sun, or 10,000 times the mass of the sun. So people have been looking for these so-called intermediate mass black holes for decades. They've been very difficult to find. There have been many published results that have been later debunked. People thought they found one, but it turned out it was something different. This potentially is one way. We're sort of on our way to forming an intermediate mass black hole. And actually, for decades ago, people proposed this idea, merging repeatedly little tiny black holes to grow a bigger black hole. This is one way these intermediate mass black holes could form, but we never observed one. So actually, this changed. This is actually about 6 months ago. It was actually pretty recently. We observed for the first time, I think very convincingly, I don't think it will be debunked. We observed an intermediate mass black hole in a globular cluster in the Milky Way. So this is in Omega Centauri. It's the most massive Milky Way globular cluster. Has a mass of around 4 million times the mass of the Sun. Very massive. They observed a few very high velocity stars in the center that essentially have velocities that are, if they weren't bound to something, they would have escaped the cluster. But they're orbiting very quickly, and you can then infer, same story that I've been telling tonight. If you observe their velocities, you can infer the mass of the thing they're orbiting, and they measure a black hole with a mass of around 10,000 solar masses. So this is really the first direct evidence for one of these intermediate mass black holes, which is sort of the, you could say, missing link between the stellar mass black holes and the supermassive black holes. So yeah, great.
One quick follow-up.
Oh, sure.
You mentioned that the globular clusters form from a collapse of molecular hydrogen. But is it possible, I thought globular clusters were very old. So did molecular hydrogen exist back then, or was the collapse from atomic hydrogen?
When the universe was very young, it was all atomic hydrogen, but molecular clouds they're called molecular clouds because of the fact that they're very cold, and when you have cold enough gas, hydrogen atoms can become bound and form molecules of hydrogen. So that's what sort of allows, this is a key feature of star formation in general. You have to have molecular hydrogen because that allows the cloud to be cold enough for gravity to take over and allow it to actually collapse and form stars. So, yeah, good question. Yes?
Hey, I have a question. During your intro, it mentioned you were a music major.
Yes. Yeah.
And so, this is not scientific, but may I ask you, what led you to study what you're studying now? Or what caused you to move away from music and into the space? And if you were to say to someone who maybe, LIGO or whatnot, what would inspire someone? Share a little bit of that. Like, what led you from music to become who you are now?
Yeah, sure. I'm happy to talk about that. So I actually, in undergrad, I actually did a double major, and I was a trumpet player. Trumpet was my specialty. So I did a double major in trumpet performance and physics. I was always really interested in both. I was a really good trumpet player when I was, in high school. So I wanted to try to study music just because it was a talent, and it was very fun, and I thought I had potential career prospects. But I always loved physics as well, so I thought I would try to do the double major. And, I just kind of, going through both, I decided physics was more, it spoke to me a little bit more. The thing I really actually liked about physics was maybe counterintuitive. I feel like I'm able to actually be much more creative as a scientist than as an orchestral musician, just because, as a scientist, you're using all sorts, even, when I make slides, it's kind of artistic, thinking about the way to combine images and the best way to tell a story as I'm, presenting things. So I find I get to exercise a lot of, creativity in a way that I would not have necessarily been able to as a musician, which is fun for me. To be frank, also, there are better career prospects as a scientist than as a musician. So anyway, the other kind of funny part of that story, so the one, positive thing I came out of my music, explorations. I met my wife, who was a much more talented musician than me. And I realized, I'm never going to be able to have a career like her. I was right, because she's actually in the LA Philharmonic now. She's a hot player in the LA Phil. so I was right to let her be the musician and let me do the science. And now we have a young son, so now my whole life goal is to make sure he's a scientist and not a musician. Or at the very least that he's a trumpet player and not a French horn player like my wife.
born with physics, right?
That's right, yeah.
But you know what? Music and physics are so highly structured. Usually, people that are really good at music are really good at the song.
Yeah, that's true. Yeah. It's very true. Other questions? Yeah.
So, try to articulate the question here as best I can. I guess I'll get to the part of the question. So what about black holes? I don't want to be too
That's a lot.
Obviously, we study everything we can in
Yeah.
space, in the galaxy and universe. Like you said, black holes, they're pretty cool relative to most things out there. Do the scientists, the astronomers, the physics folks, is there something about black holes that there's a hypothetical, some sort of a guess as to the potential danger of black holes, the potential positive potential of black holes? Like, what is there about black holes that might be relevant to us?
Yeah, okay.
If anything?
Yeah, it's a great question. So I can give you a couple concrete answers. So one very concrete answer. So of course, Einstein developed these theories. The science of black holes is really Einstein's theory of general relativity. But she initially developed, it was completely theoretical. It was designed to explain, these types of very esoteric things in astronomy. So as it turns out, the theory of general relativity is now essential for measuring precise orbits of satellites around Earth. So it was originally developed as just, Einstein having fun and developing this theory. But all of the satellite technology we have now absolutely relies on these theories developed by Einstein. I mean, this is, an argument for basic science in general, is we're pushing the boundaries of our knowledge with, the idea to, it's not going to have necessarily an immediate payoff, like if I was doing materials, science research or something, which is, has a very, immediate benefit in terms of real world applications. But we're pushing the boundaries of our knowledge to develop theories and insights that will have implications down the road that we can't even think of yet. So that's a very classic example. Many people would give you the same answer if they ask, but it's a very classic example. Maybe not so much black holes, but this is another thing I think about a lot. So astronomy is a laboratory for studying the most extreme physics in the universe in ways that we can never study on Earth because astronomy requires these incredibly massive objects to create such strong and high temperatures and extreme environments. We can never recreate these in a laboratory. So, I spent the summer in undergrad at the Princeton Plasma Physics Lab, which was trying to develop nuclear fusion technology. They're using astronomy as an application to try to learn about this stuff in ways that we can't do in a lab. So that's another very immediate benefit. We're researching matter at such a extreme level that it almost certainly is going to have implications down the road, in terms of energy research and things like this. There's a few others, but yeah, it's a great question. It's a very important question actually to ask is why. And then of course, it's fun. It's there. It's like, these things are real and they're out in the universe. So who wouldn't want to know how it's happening and how it's forming? So.
What I'm understanding from what you're saying, like Einstein discovered things 100 years, whatever it was, right? But he didn't even know the implications down the line decades.
And there's so many examples in science of this.
Learning for learning's sake.
Yeah.
For the potential benefit that we don't even know about.
The theory of quantum mechanics was the same. It was developed 100 years ago, and it was completely theoretical physics at the time, and now it's used everywhere in science for all technology. So there's tons of examples of this. So I should say I'll answer questions for ever. So it's going to be up to the people in the back to end it when you want to end it, because I will literally go on forever. I have to answer questions. Yeah.
So I want to involve learning violation of limitations. Could these masses contribute directly?
Okay, yeah, great question. You mean like these black holes, like in?
I mean, they're kind of distributed outside.
Yes, yeah. No, because there's not enough. There's not anywhere near enough mass. Like you need to do all the black holes and globular clusters and speed them out into the galaxy. Nowhere near enough mass. There's one of the theories for dark matter is maybe dark matter is just a bunch of little tiny black holes, like moon-sized black holes that you couldn't detect otherwise, and they would exert gravitational influence and maybe could explain dark matter, but yeah. So, I mean, I think that this question, what is dark matter, is one of the biggest unsolved mysteries in astronomy. I think that there's a chance it will be solved in my lifetime, but I wouldn't bet the house on it. I think that's the next big question in astronomy is what is dark matter? Many people are working really hard on that. Yeah.
I excel at asking pedestrian questions. How do you answer this really fast? I really want to know. Back in the early part of your presentation, you mentioned binary stars. At what point did the term binary star enter the lexicon of astronomy?
Oh, that's a great question. I have no idea what the answer to that is. Over 100 years ago, for sure.
I'm thinking like the early mid-30s.
I think it was before that, because we've known of binary stars. Again, because almost half of stars are in binaries. We've known of binary stars for quite a while. So it's the idea of binary stars has been around for certainly before I was born. Yeah.
You described the evolutionary cycle of stars with globular clusters and also black holes. What about the future evolutionary cycle of the globular clusters themselves? What are they going to be like? What are they going to be made of?
Okay, so I kind of talked about this a little bit, this idea of mass segregation and things sinking to the center of gravitational potential. So I talked about stars in a cluster sinking to the center of their cluster. Well, globular clusters are in the halo of the Milky Way. Everything in astronomy, as you'll realize, is the same thing. It's an n-body population of things governed by gravity. So a globular cluster is like a scale-up star. A galaxy kind of is like a scale-up globular cluster. So the globular clusters in the Milky Way are all slowly spiraling into the center of the Milky Way, where they eventually will be torn apart by the tidal field of the Milky Way galaxy. So I think this is maybe one of the ways that I talked about this at the very beginning. The center of the galaxy has this very dense bulge. And actually, in the very center of the Milky Way, there's a nuclear star cluster, which is sort of an ultra-dense version of a globular cluster. We think this is actually assembled from globular clusters that, earlier throughout the history of the Milky Way spiraled in and were disrupted and sort of built up this very dense central region. So that's one fate. The other fate of globular clusters, for globular clusters that are really far out from the center of the Milky Way, they won't really have time to spiral in. They will eventually reach core collapse, like I said, all clusters do. As the core collapses of a cluster, the outer parts expand, kind of analogous to a star. The center of a star collapses and the outer envelope expands, becomes a giant. So the fate of these clusters is essentially eventually to just shoot everything out, all the stars out into the halo of the Milky Way. And all that you'll be left with is that very dense central region, which has some black holes and also some white dwarfs and neutron stars.
Yeah, so they will also contain fewer black holes, but the black holes they do contain what will be much more massive.
Yep.
Thank you.
So we're gonna just take one more shoot verification.
Okay, sounds good.
So early on in the presentation, you showed like the binary stars and then how a third star comes in and causes all of this chaos in the rotation. Then when we talked about black hole mergers, it seems like binary was the only word used, and it almost seems even on this like sequential, like two at a time, and then another one can be added. I realize that black holes are maybe a little bit more sparse than stars, but have we done any research or theorized if there's like additional chaos if 3 black holes merge at the same time, or 4 or 5, or what like amplification that adds to this?
Yeah. So this happens. So there's a lot of details I kind of glossed over. So I showed toward the beginning this sort of group of 3 stars in a sort of chaotic 3-body encounter, right? So in the center of that black hole subsystem, 3-body encounters between 3 black holes happen all the time. Those are actually the main engine for forming those black hole binary mergers that create gravitational wave sources. Now, all 3 black holes usually don't merge at once. That maybe could happen to be very rare. But there's those sort of chaotic 3-body encounters where the black holes are gravitationally interacting with each other, those are happening all the time in that sense, in that very dense region. So yeah, also fun to think about when you 3 black holes doing that sort of chaotic dance. It's something we think is actually ongoing in the center of these systems. Okay, should we stop there? And I'll stick around and answer some more questions if people want to chat a little bit longer. So thanks again for coming.